Okay, hi everyone. My name is Emma Fost, and today I'm going to be going over lecture slides from lecture 22, and we're going to be going over mixtures of gases. So there are four main topics that I'm going to be talking about. The first one is ideal gas law. The second is partial pressures. The third is mole fractions, and the fourth is van der Waals equation. So to start with, we talked about in the previous lecture ideal gas laws. So in this lecture, we did more of expanding this into derivations relating to density and molar mass. So that's kind of what I'm going to be talking about. So to start with, we're going to start with what we already know, and we know that PV equals nRT. That's the ideal gas law equation right here. And then we know that the molar mass equals the mass over the moles, grams per moles, and that is represented by m over n. And we know that the density equals the mass divided by the volume. So let's start by deriving this molar mass equation. So to start with, we're going to go PV equals nRT. And so as you can see from the similarities between this equation and this one right here, they both include an n. So what I'm going to do is I'm going to solve this one for n. All right, so it would just be PV over RT equals n. And then I'm going to do the same for this molar mass equation, equals the mass over the moles, and I'm just going to multiply that. So then n equals m over n. So from here, I can plug in this n right here. So then PV over RT equals the mass over the molar mass. And so from here, I'm just going to straighten it all out, and what it'll end up looking like is m equals the mass times r, just our constant, times temperature over pressure times volume. And we're going to see that this is actually going to come up in some of the practice test problems, and it's just a way to represent, different questions are going to ask you things in different ways, so it's important to know the relationships between this ideal gas law equation and the molar mass and density. So now that we have derived this equation, we're going to derive the density equation. All right, and so right here we see that density equals mass divided by volume. So we're going to use a similar process, and we're going to take this PV equals nRT, and we're going to solve it for volume. So volume equals nRT over P. All right, and then I'm going to do the same for density. So density equals mass divided by volume. And then we're going to solve for volume. So volume equals mass over density. All right, and then I will set them equal to each other. So mass over density equals the moles times the R constant times the temperature over pressure. And then to solve for density, you can rearrange it and kind of solve it for density. And one of the things that we are also going to want to notice is that in this derivation, there is an m. So we are going to want to look for this m over n in this equation. So, I'm just going to skip some of the math and just me. It turns into that. We just have to turn that recognize the m over n that'll eventually come, and then it'll turn into this density equation. So as you can tell from this, it's really important to know the relationships. I think as long as you know these relationships, you should be able to get to these on the test. I'm not really exactly planning on memorizing these. I'm just going to stick with what I know, and then I'm going to be able to find it based on these relationships right here that I just derived. So kind of know how to manipulate equations, and I think that'll be a huge help on the test. And so now I'm going to move on to partial pressures. So here we have a Dalton, and he said that the total pressure in a given volume at a constant temperature is going to equal the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, and so on. And we can also see this represented in this equation, where the total pressure equals the total sum of all the moles times the constant T over V. And I mean, we can really see that this is just PV equals nRT. And it's just going to stay the same. Even if there's multiple gases, you're just going to take the number of moles of all of the gases. And we have to remember that moles is a representation of the particles. I mean, it's just telling you how many particles it is. So it makes sense that it's not really going to matter what the element is, what they are. It's just going to matter how many of them they are. It's just not going to make a huge difference if they're nitrogen or oxygen. Of course, if we're not really taking into account like intermolecular forces or anything like that. But so here I have I'm going to have a bunch of different colors of these at the end, and these are each going to represent kind of multiple atoms, I guess. And as you can see, they are in a contained volume. We are going to assume that as I add more elements, that it's going to stay at that same constant volume and the same constant temperature. And the only thing that we're changing is the moles. And we're going to be changing we're going to be using different types of elements. And we're going to see how it doesn't really matter. The pressure is not going to do funny things depending on the different elements that we're using. So here I have this, and then we are going to add another one and another one. So the total pressure, oops, I have some marks on here. The total pressure is going to equal the total amount of moles. So the total, I mean, let's just say that there's 1 mole of each element. Sorry, I have something like these decorations. That's like not important. So we have 3 moles in total because we have a mole of the white ones, a mole of the gray ones, and the mole of these black ones. So we have 3 moles in total. And we're going to use the R's constant that we got from the formula chart. So I'm just going to leave it in terms of R for right now. And then temperature, let's just say it's at 1 degree Kelvin. And then the total volume, we'll just say 1 liter. And so the total pressure is going to equal 3R. And of course, in practical terms, we would definitely multiply out that R, but just for simplicity, I'm just going to leave it. And so now we're going to move on and talk about mole fractions. And a mole fraction is the ratio between the moles of one component and the total moles present. So we can use the same representation that I was using to explain the last one. And if 5 of these atoms represent 1 mole, so we have 1 mole of each of the elements like last time, what is the mole fraction of the following atom? So we're going to look at this black one. So we have the mole fraction equals, and it's going to be the number of moles of the given element or compound divided by the total number of moles. So as we determined last time, we have 3 moles. And we have 1 mole of this black one. So 1/3 would be our mole fraction. And we can relate this to partial pressures like we learned before. And so if you remember from our just 2 examples ago, the total pressure was 3R, right? And then we're going to multiply it by this X, which is our mole fraction. And we said that was 1/3 equals pressure. So then our pressure would just equal 1R. And this is just handy to know the relationship between the partial pressures and total pressure, because if we know the mole fraction and the total pressure, then we can really see what that one element is contributing. So that's really cool. And so now I'm going to talk about van der Waals equation. And as we know, the ideal gas law is not going to account for all of the gases. It's exactly what it says it is. It's for ideal gases. It's not meant for all of them. And gases are going to behave not ideally if there's intermolecular forces that's acting between them. So that means if it's at a low pressure, high temperature, it's going to act ideally. But say it's at a really high pressure and a low temperature, that means that all of the atoms are going to be really close together and they're going to be interacting with each other. And it's just ideal gas law just doesn't take into account the atoms interacting with each other. And so that's where van der Waals equation comes in. So here's the equation, and we can see how it relates to ideal gas law. And this is van der Waals. So here we have the pressure plus the number of, or the moles squared times A. And just for reference, there's an A and B value. Here's like a chart of a bunch of different ones, A and B values. This is just a few of them. There's separate A and B values for every single element, and they will be given to us. So that's not as important, but we do want to recognize that the A is adjusting for the pressure and the B is adjusting for the volume. So going over this again, it's the pressure plus the moles squared times that A value for the volume squared times the volume minus the moles times the B constant. And then the last part is the same as the ideal gas law, and that just stays the same. So the best way to do this is actually probably just going to be to practice it. So here, using van der Waals equation, calculate the temperature of 20 moles of helium in a 20 liter container at 120 atmospheres and here's our A and B values, and here is van der Waals equation. So we have our pressure, and our pressure is 120 plus the moles, and we have 20 moles. So 20 squared times A, which is 0.0341 equals, oh, nope, I'm gonna put those in parentheses. Oh, nope, I forgot the V. So divided by the volume squared, which is just gonna be 20 squared times the volume, which is 20 again, minus the moles, which is 20 times 0.0237. And looking at these A and B values, they are actually relatively very small. And so this gas, helium, is actually gonna behave pretty similarly to an ideal gas, because these numbers just aren't that big. You're not going to be really adding or subtracting that big of a number for it. So I mean, honestly, ideal gas law is going to be a pretty accurate representation, and we might even do this example with ideal gas law to kind of compare the two. So I'm just going to throw this in my calculator. Hopefully I calculate this right. So we have 400, oops. Oh, I guess we can just, these won't always be the same, but I'll just cancel those out. So it'd be 120.0341 times, I'll have to multiply this one out. So 20 times 0.0237 equals 20 minus 0.474. And so 20 minus 0.474 is going to equal 19.526 times 120 times 0.0341. Okay, and that's going to equal 2,343.78. Okay, hi guys, I am back. It's been a couple months for me and a few seconds for you, but I'm just going to finish up this video with a couple more practice problems from the problem sets. So, yep, and so we'll just get started with this question. What is meant by standard temperature and pressure, STP? And that means that it's at approximately 1 atmosphere pressure and it's at 0 degrees Celsius, which translates to about 273 degrees Kelvin. So make sure to remember that. And since I know the final is coming up, make sure not to get that confused with the other standard units that we learn later on. And so another thing to remember is what is the volume of 1 mole of an ideal gas at STP, and does it matter what gas? So it's not going to matter what gas, and it's going to be 22.4 liters. So make sure to remember that. And now I'll move on to the next problem. All right, so apparently after this part, my audio decided to cut out. We love that. And so I'm just going to work on what is the density in grams per liter of sulfur hexafluoride at 227 degrees Celsius and 2 atmospheres of pressure. So I'm starting with the equation for density, and density equals the mass divided by the volume. And I'm going to do the mass equals the number, or the amount of moles times the molar mass. And then for velocity, or not velocity, volume at in the denominator, I'm going to derive an equation from PV equals nRT and solve for volume, and then plug that into the denominator. And at that point, I'm just going to simplify. I'm bringing the pressure up to the numerator at this point. And now I'm just going to cancel out the moles to get the molar mass times the pressure divided by R times temperature. And so at this point, it's basically just a plug and chug. So for the molar mass, I did that off camera, I guess, for sulfur hexafluoride. And so, oops, I wrote 5 for some reason. It's supposed to be 6. Ah, there I am fixing it. Cool. And so the molar mass of that is, let's see, it's 146 grams per mole. I should really be writing my units along with this. However, I am not, but you should. And so I have 146 grams per mole times the 2 atmospheres that it gives us in the equation, divided by H, which is the constant on the equation sheet, and then times 500 degrees Kelvin, which is the equivalent to 227 degrees Celsius plus the 273. I just converted that. Wait, I haven't written 500. It's almost there, you guys. Okay, times 500. And then you just plug that into your calculator and you get 7.12 grams per liter. Alright, up next we have an unknown gas is pumped into a 2.15184 liter container that is already filled with some O2. The unknown gas exerts a partial pressure of 2.3 atmospheres. If the total pressure exerted by both gases is 11.2 atmospheres, what is the mole fraction of the unknown gas? Now, unfortunately, they give us some unwanted information, which is the liters of gas. We are just going to use this equation that I have here, which is that the partial pressure of the gas equals the mole fraction of the gas times the total pressure of the gas. And so what it gives us is it gives us the total pressure and the partial pressure, and we're solving for that mole fraction. So I'm just going to simplify that equation, and so the mole fraction is going to equal the pressure of the gas divided by the total pressure. And then, once again, just plug and chug. We have the 2.3 atmospheres divided by 11.2, and there we go. That's what it equals. I think it ends up being 0.205, and best of luck on the final. Thank you for tuning in to my review.